Hi, everybody, and welcome back to another video regarding some concepts related to ideal gases. This third video is going to be regarding specific heats. So hold on to your hats. This is definitely one that there's some complexity to it, and you as a student and then practicing engineer are going to need to learn how to make decisions about using specific heats on ideal gases. So here we go. All right, so the title of this is Getting Started Using Specific Heat or Specific Heats with Ideal Gases. Little roadmap, because this is going to be kind of complex this time. We'll review the basic definition of C sub P and C sub V for all substances. Then two key behaviors of ideal gases, because that's our focus, dealing with ideal gases. I'm going to talk about a key relationship between C sub P and C sub V. Those are two specific heats for an ideal gas. Then we're going to move down to using CP and CV with ideal gas specific engineering situations. Now, a little complexity is added. Sometimes we can use C sub P as a constant. Sometimes we must use C sub P as a variable. Well, when do we do that? I'm going to talk about that in detail. I'm going to give you a couple of simple example problems to illustrate using specific heats for ideal gases. And then I'm going to quickly mention some classic student misconceptions about using specific heat and ideal gases in general. So here we go. Basic definition of C sub P and C sub V. Here it is. Now, it's sort of imposing look. C sub V is defined as the partial derivative of U with respect to T holding V constant. Say it again. This variable, C sub V, it's called du dt at constant V, partial derivative. Now, next, C sub P, the partial derivative of enthalpy with respect to temperature holding P constant. C sub P is dH dt at constant P. It's a partial derivative. So we find that there's not a lot we can do with this analytically. Now, want to chase you into your book. Section 3.9 says introducing specific heats, C sub V, C sub P. I need you to at least go to your textbook and browse that section to get a deeper understanding of the basics of these. Now, just some words about, you see, I've been calling this C sub V and C sub P, and I'm going to continue doing that. Instructors may say, no, C sub V is called the constant volume specific heat. And some may say C sub P is called the constant pressure specific heat. And the reason of that is because the nature of this general definition, notice C sub V holds V constant in doing some mathematics on the partial derivative. C sub P, it holds pressure constant for doing some mathematics on the partial derivative. So that's how come folks refer to it in that way, but I tend to not. So let me give you some whys I don't do that. Here's a way to maintain your sanity. How to pronounce C sub P and C sub V. Pronounce C sub V as C sub P. This variable pronounced C sub V. Now, both of these are specific heats. They're both called specific heats. It's easy to get them confused. And so this is just my opinion. And so you can take it or leave it, but I suggest that you pronounce this variable as C sub P and this variable as C sub V. That's my recommendation. So then the next logical thing is, well, when am I going to use these things? When am I going to use this in engineering problem solving? And the answer is simple. we're going to use these when we need to either find delta U or delta H. Those are the times we're going to use those. Delta U, U2 minus U1. Delta H, H2 minus H1. Okay, that's when we're going to use them. But there's only a couple of conditions when we're going to use CP and CV in calculating these things. So we're only going to, that's when we need to use them, but only when our substance is either a compressed liquid or solid. That's situation one. We're going to talk a little bit about that. Or when our substance is an ideal gas. And we're going to talk a lot about that. So let's get this part. When we have a compressed liquid or a solid and we're looking for delta U or delta H, let's get that out of the way quickly. I want to suggest you go to your textbook, section 310, that discusses situations where you have engineering problems related to liquids or solids. Okay, so you must read this section. And so, and here's the big reveal. When you have liquids or solids, delta U is equal to what the textbook called C times delta T. And I've got to move my zoom bar here. And enthalpy change, H2 minus H1, is simply C times T2 minus T1. And there you go. So that's pretty simple. Let me go to the next slide to give the big reveal on the C specific heat for liquids and solids. Okay. It turns out that for liquids and solids, C sub P equals C sub V, only for liquids and solids, and the textbook calls that C. And so you can say, okay, if I've got a liquid and solid, I'm going to go to table A19, and I'm going to look up a specific heat value that corresponds to my substance. Notice here it's arranged by solids and liquids. But anyway, it's a simple matter of looking up a specific heat, C, using it times delta T, and that's going to be the change in internal energy and or the change in enthalpy. Okay, so that dispenses with liquids and solids. Now let's move on to the purpose of this, talking about using C sub P and C sub V for ideal gas calculations. Okay, so here's two key behaviors of an ideal gas. One is the ideal gas equation of state that you now know by heart. You know this by heart. P times little v is equal to RT. Pressure times specific volume is equal to R, the gas constant, times T in absolute temperature. That's one you know by heart. Second thing, haven't introduced it yet, but your textbook reading is going to clearly explain that the internal energy and the enthalpy, U and H, for ideal gases depend only on temperature, does not depend on pressure. That's dramatically different than phase change substances like steam. And so mathematically, let's write this out. U equals U of T only. Internal energy U is a function of temperature only. Enthalpy, H. H is a function of T only. So that's what that means. And that's really a good result. So I'm going to move ahead to explain to you functionally what can you do with this. Very valuable. Okay. Well, it allows us to simplify the basic definition. So let's go through our math understanding. We started with a partial derivative. Now, for an ideal gas, it turns out that internal energy and enthalpy are functions only of temperature. So this partial derivative, no longer, you don't have to be so careful in doing the math. If U is a function of T only, this partial derivative turns into an ordinary derivative that you're more familiar with dealing with. So for an ideal gas, C sub V is simply du dt. And C sub P is simply dH dt. Now you're getting close to some math that you can perform. So let's look at moving the dt over to the other side, the dt to the other side, so that we can integrate both sides and calculate delta U and delta H. So here we go to the next step. delta U is U2 minus U1. Well, that's the integral of CV dt evaluated from T1 to T2. And delta H, H2 minus H1, is integral of CP dt from T1 to T2. This is something to commit to memory. So this is another thing to commit to memory. Delta U for an ideal gas is the integral of CV dt. And delta H is the integral of CP dt. That is worth memorizing. That's true for all ideal gases. Okay, so I'm going to pause a little bit because I'm sort of blazing through here. Okay, let's recap this slide. We started with a partial derivative definition of CP and CV. Then we recognized that for an ideal gas, U and H depend only on temperature, so we moved into a ordinary differential equation definition. And then we say, in engineering, we're going to have to calculate delta U and or delta H lots of times. And so then we manipulate this into a differential equation and integrate it to get delta U is the integral of CV dt, and delta H is the integral of CP dt. Okay. Another key relationship between CP and CV for ideal gases. Again, your textbook does a superb job of developing this. I'm just giving you the result. And that is that CP, which is can be a function of temperature, can be a formula based on temperature, minus CV, which also can be a formula based on temperature. But if you subtract both of those, you subtract CV from CP, you get a constant, which is R, the gas constant. CP minus CV is equal to R. That, you got to commit this to memory. CP minus CV is equal to R. R is the gas constant, R bar over the molecular weight. Okay. So the big conclusion is that CP and CV can be variable. They can be formulas, functions of temperature. Subtract CV from CP, you still get a constant. Okay. Now, one more note for this slide. Notice here, when you see this equation, you should know the units of R. What are the units of R? Well, R in SI, kilojoules per kilogram degree K. In English, foot-pounds force per pound mass degree R. And so therefore, with your eye, CP and CV have those units too. They must have consistent units with R. That's a big conclusion, a big and important conclusion. CP and CV have the same units as R, kilojoules per kilogram degree K. Now, okay, now we're getting into some details. So don't panic. We aren't getting into details. It's possible. We pray for CP and or CV being a constant number. That's what we hope we can have for our engineering problems. We would love it. We would love CP to be a number. We'd love CV to be a number because why? Because if we look at our equation, our integral equation for delta U, integral of CV dt, if CV is a number, I can pull it out of the integral, and I've got delta U is CV times delta T. Easy. And I've got delta H, pull that out of the integral. Delta H is simply CP, a number, times delta T. Easy, easy, easy. That's what we're praying for. Okay. It is possible sometimes, though, that CP and CV are variable. In other words, they're a formula based on temperature only, like maybe a polynomial based on temperature. But it is possible that CP can be a variable expression. That makes the integral tougher, doesn't it? So we come down here, and now we can't simplify our expression. Delta U is the integral of CV dt. Delta H is the integral of CP dt. Yeah, so we're going to need a formula for these expressions in order to get a number for U2 minus U1 or H2 minus H1. Does this make sense? So we're praying for constant. There will be times where CP is a variable, and we got more work to do. Okay, next slide. Logicals, okay. When can I say that CP is a constant? When must I say CP is a variable? And so I've got two examples to illustrate that. So you can say CP is a constant value when the temperature change for your ideal gas is small. So for example, I've got let's say I'm in the wintertime, okay? Let's say the room temperature is 23, but I want it to be 25. I'm going to add heat to the room. I'm only going to heat the room up by 2 degrees C. That's a small temperature difference. And so that's going to be an example of where we're going to treat C sub P and C sub V. Remember, CP minus CV is equal to R. So either way. But for a small temperature difference, we're going to treat CP as a constant. And if we were looking for change in internal energy, we would treat CV as a constant. Next example, you must say that CP is variable. In other words, it's a formula, a function of temperature, when the temperature change for your ideal gas is a significant value. When you have a large change in temperature. Here's an example. I'm working in a manufacturing plant, and I'm in one of my jobs is to heat up outside air from 25 degrees C. And for my process, I need that air to be 500 degrees C. I need extremely heated air. That would be a clear case where we would probably want to treat air as an ideal gas with variable specific heat. Then we got a little more difficulty. Now, here's a fun fact that I've got in green. For monatomic gases, and those are argon, neon, and helium, CP and therefore CV. CP and CV are always constant numbers. You can look them up. Now, what's the downside? How many engineering problems do we have when we're dealing with argon, neon, and helium? The answer is not very much. Maybe if you're in the balloon blowing up business, you're working with helium. Yeah. If you're in the torch business, blowtorch business, we use argon as an inert gas that shields the blowtorch process. Okay, so those are examples of using monatomic gases, but obviously in the engineering world that I worked in, I didn't work with monatomic gases much at all. Now, I'm getting off track. The yellow box, your instructor is going to be giving you additional guidance on how to make these decisions. So do not panic that you're on an island. Your instructor will be giving you additional guidance on when can I use CP and CV as constant numbers, and when do I have to use CP and CV as variable. Instructor will give you more, should give you more. If instructor does not give you more guidance, ask for it. Okay, so I want to, so many of our engineering problems involve air. Because air surrounds us, it's we use it in in manufacturing all the time. We're always using and dealing with air as engineers. Now, we always treat air as an ideal gas. Always, always, always in our engineering problem solving. 99.9% of the time, we treat air as an ideal gas. Next step, we have to make a decision on how to model CP and or CV. Will we treat it as a constant number, or must we treat it as a variable, or in other words, a formula as a function of temperature? So we're going to treat it as constant if our temperature change is small. If our temperature change is significant, we're going to have to go to more complex approaches. And again, your instructor should give you guidance on this. If not, ask. All right, so now for some details. When we can model the gas as an ideal gas with constant specific heat, in other words, the temperature change of the process is small. We're going to go to A20 because notice, let's look at A20. You've got air, you've got nitrogen, you've got oxygen. Carbon dioxide, you've got a pick list of substances that are all ideal gases, okay? You need to decide on what's my nominal average process temperature. Answer would be take the beginning temperature, the end temperature, average it. That's your average process temperature. You're going to look up your temperature here, and it looks like in degrees K, and then you will read over one. So that's just one average process temperature. Let's say it's 450 degrees K. You'll read over and you'll pick off a number. What if it's between 450 and 500? Then you have to interpolate, but you're excellent interpolators now. Okay, that's how you get a single number for specific heat for any ideal gas. That's how you do that when we're going to treat any ideal gas with constant specific heat. Go to table A20. Now, next slide. So now we're looking at air only, There's other ideal gases, carbon dioxide, carbon monoxide, but let's look at air only. When we must treat air as an ideal gas, but we have a huge temperature difference, we've got to use variable specific heat. Now, let's go to table A22, a handy table so you don't have to integrate. Handy table. This is called the air tables, okay? Table A22 applies only to the gas, ideal gas air, okay? Mixture of nitrogen and oxygen, we breathe it, okay? And so then H and U are functions of temperature only. So you go down your left column, you find your temperature, let's say it's 300, and read across and write down H and write down U, okay? And so, you get the idea. Okay, that gives you a single number for H for 300. If your temperature is 302 instead of 300, you got to interpolate for H or U depending on what you need. Okay, so in the green box here, the complex integration of variable specific heat has been performed for you nicely and tabulated for you. This is A22 applies to air. Let's say you've got some other gas other than air, like carbon dioxide or carbon monoxide or nitrogen, okay? You're going to go to table A23. It's the same idea. Here's your temperature tabulation. Here's your enthalpy. Here's your internal energy. But notice here the units. So you have to look very closely on this slide, but the units are molar, kilojoules per kilomole. Be very careful in this table A23. So you've got to divide these numbers by the molecular weight to get your enthalpy and internal energy values in terms of kilojoules per kilogram. Same idea. The complex integration has been performed for you when you have ideal gas substances other than air. I know I'm blazing along, but this is just to give, you can go back and look at the video. You can look at the static PowerPoint to refresh your memory when you need to. Okay, there will be probably a couple of homework problems. I'd be very surprised if you see this on a quiz or test, but there probably will be a couple of homework problems that your instructor assigns you where you need to use a formula for specific heat. Okay, and integrate it to find delta H or delta U. And this is the way you do it. You're going to go, when we're directed to use an ideal gas equation with a mathematical expression, Cp is a function of temperature. Now, what if you need Cv as a function of temperature? I remember that Cp minus Cv is equal to R. So let's see, Cp minus Cv is equal to R. So if I've got a mathematical expression for Cp, I can see that Cv expression is simply Cp minus R, minus the constant R. Okay. But let's look at this a little bit. So this table A21 gives you a bunch of coefficients, alpha, beta, gamma, delta, and epsilon for a polynomial expression, a fourth order polynomial expression. So this gives you the formula. It discloses the formula then for you to go in and integrate by hand to get a numerical result integrated from 1 to 2. This can be it can be tedious, but you can do it. Tedious, but you can do it. Okay, now going to graduate school at the graduate level, in a graduate level thermo class, you will be doing this. It'll still be tedious, but you'll be doing more of it. All right. So be very careful with the units as well. I'm not going to save time. I'm not going to delve into the units, but do see that notice here the bars. These are all going to be in molar units. Molar units. Okay, I've thrown a lot out at you. I don't want you to panic, but you're probably seeing I've got to make some engineering decisions here. I'm going to be expected to make some engineering decisions with some guidance from my instructor. But you might worry a little bit of how do I decide? I've got an ideal gas, but how do I decide if I've got constant specific heat? Easy. Or variable specific heat? Tough. Okay. Constant specific heat. Okay. I've tried to create a decision tree for you. Step 1. Do I have an ideal gas? If the answer is yes, continue on. If no, go back to phase change tables. So let's say, so yes, I have an ideal gas. Do I have air? If yes, you've only got to answer 2 questions. Have I got a small delta T? Great, use constant specific heat. You got it made. Delta H is Cp times delta T. Delta U is Cv times delta T. I have air, but I've got a huge temperature change from 1 to 2. I'm going to have to use Cp, and in that case, I'll use table A22. Okay, that makes it pretty easy. Decision tree. Okay, I don't have air, but I have a monatomic gas. I've either got helium, neon, or argon. That's easy. Cp is always constant, and therefore Cv is always constant. Do I have something other than air or a monatomic gas? Well, the same idea, small delta T, use constant specific heat. Big delta T, you've got 2 choices. One is you can use table A23 to look up tabulated values in which someone did the integrals for you, or your instructor may direct you to go all the way back to the analytical formulas and perform the integral. And that's the case where you're going to go to A21, write down the coefficients for the 4th order polynomial, and perform the integral. So a lot of students panic in this situation. It's my hope that you can go back to this decision tree so you don't panic on homework problems, and at least you can keep this in your mind so as not to panic in test and quiz situations. So obviously, this decision tree doesn't look like anything that you'd put on a formula sheet, does it? So you'd have to have this. You'd have to have some practice with this decision tree in your mind. I need to go live, so I'll show you how to find this PowerPoint file if you wish to go and look at the static slides, because we've blazed through this video. So I'm going to stop sharing. Okay, I'm going to minimize my screen. Whoops. Okay. I keep making this mistake all the time, don't I? I got to keep sharing my screen. Okay. I've got to escape out of PowerPoint. I've got to go to my browser. Okay, go to Jay's Toolbox. Let's go to Files. How to find this PowerPoint file. We're going to go to Tutoring and this folder called PowerPoint for Videos. And this video is IdealGas03. So you're just going to click on IdealGas03, and you can possess this PowerPoint on your own. You can possess it, save it to your PC. Okay, now back to the PowerPoint. Okay, here we go again. We're at a good pausing point. Let's check our roadmap. We talked about the basic partial derivative definition of CP and CV. And I did some talking about, what would you call these things? I suggest you call them CP and CV. They're both called specific heats. Then we talked two key behaviors for ideal gases. One was the ideal gas equation of state, and the other was that enthalpy and internal energy depend on temperature only. Talked about key relationship between CP and CV for an ideal gas. That was something to remember. CP minus CV always equals R. R is the gas constant for each ideal gas. CP minus CV is R. Okay. Then we talk. Now we've got engineering problems to solve. We will use CP and CV in those computations when we want to find delta U, CV, and delta H, we use CP. Okay. Then we got to make another decision. So either way, even though we've got ideal gases, we have to decide if we're going to model specific heat as constant, one single number, or a variable, a formula, or lookup tables. So that's what we've covered. We're really coming down the home stretch. Got that scratchy nose again. Example 1. I need to heat the air in a room from 65 degrees F to 72 degrees F. The pressure in the room is 14.7 psia. It's a lot like the atmosphere. What will be the change in enthalpy, delta H, for the air for this process? And what is the density of the air at the beginning of the process? Very reasonable, simple problem to do. And also I see that, look, I'm just heating the air in the room from 65 to 72. That's looks like 7 degrees F. That's not too much. So we're going to treat air as an ideal gas with constant specific heat. So we're going to write that down on our homework solution. Okay, air modeled as an ideal gas with constant specific heat, since the temperature change is small. We will use the ideal gas equation of state to determine the density. We'll determine the average process temperature. We're just going to average T1 and T2 and then look up a single value for C sub P. Then we'll apply this expression below for the enthalpy change with constant specific heat. So just to drag it out, delta H, we're looking for H2 minus H1. It's the integral of Cp dt. For this problem, we're going to treat Cp as a constant. We'll pull it out of the integral. So we've got Cp times delta T is delta H. Here's the numerics of the problem. I wrote down T1 and I added 460 to it in case I need absolute temperature. I wrote down P1 and I immediately converted that to pounds per square foot. Looking ahead, I'm going to use the ideal gas equation of state, and I'm going to use this expression for density. Rho is P over RT. I've got that in my head. So if you don't have this in your head, rho is P over RT, you can start at the basic definition, okay? Get it into intensive property form, P times little v is RT, and then recognize V as 1 over rho. Rho is P over RT. All right, so looking ahead, I know I'm going to need pressure in pounds per square foot. I did the same thing with T2. Okay, let's see. I need the R for air. R bar, 1545. Molecular weight, 28.97. Should have that in your head. So R for air, 53.33. Okay. So rho, the density at the starting point, rho 1 is 0.0756 pounds mass per cubic foot. That gets you halfway through the problem. Average process temperatures, 68.5. And now you got to go and eyeball table A20. Okay, well, we're going to go and eyeball table A20 here in just a second. And we're going to find that CP is 0.24 BTUs per pound mass degree R. We're going to plug and chug. Delta H is CP delta T, and we're going to get 1.68 with the units BTUs per pound mass, energy per pound. That's delta H, energy, BTUs per pound. Got it. Let's go and see where we got 0.24 from. Our starting temperature 65, ending temperature 72. Okay, so now we're at table A20E, specific heats for gases. We've got air. Okay, so I've got temperatures tabulated, 40 and 100. Well, both of my temperatures are in between those, and C sub P is 0.24 for both of those. And so I don't have to really do any interpolation at all. By my eyes, I say CP is 0.24 for my process. There it is. Easy. Okay, great. So that tells you how to get CP is 0.24 for air, kind of at room conditions. There you go. Example 2. I've got a manufacturing process that I'm in charge of or I'm analyzing, and I've got to heat air from 65 degrees F all the way up to 850 degrees F. Now that is hot. Compare the change in internal energy, delta U, for this process using 2 models for an ideal gas. So now we're going to model air as an ideal gas, period. But we've got to decide. And here, in this example, we want to compare. We want to use both models for specific heat, constant and variable, and we want to compare those numerical results. This is an illustrative type example, all right? Here's our approach. Air is an ideal gas. We're just going to write that down to start with. Okay, so the next thing, we'll determine a single value for C sub V at the average process temperature for the constant specific heat model. So we'll average the 2 temperatures and we'll evaluate C sub V at that temperature in a table. For variable specific heat, we've got air, so we're going to use those air tables. Forget that integration stuff with the formula. Let's just go to the air tables. We're going to look up 2 values. We're going to look up U2 and we're going to look up U1, and we will subtract the 2. And what that means is we're using the variable specific heat model. And then we'll compare those 2 numerically. So notice here, here is my expression for this first bullet item, ideal gas with constant specific heat. All right, so here's the numerics. I've boxed out our model for constant specific heat, and then I've boxed out doing this with variable specific heat. So let's look at constant specific heat first. I wrote down the initial temperature and I converted it to absolute temperature in case I need it. Second temperature converted to absolute in case I need it. And the average degrees F, I looked ahead, and remember on table A20, it's tabulated in terms of degrees F. So I averaged the 2 temperatures in degrees F, 457.5. Now, there's no, in table A20, we're not going to have a 457.5. And so I looked up C sub V. I wrote down C sub V at 400 and 500, the 2 temperatures that straddle 457, and do a linear interpolation between these 2 numbers to get CV is 0.173. So now it's plug and chug, right? We've got CV as a number, so we're looking for delta U. It's CV times delta T, or 135.45 BTUs per pound mass. Now, a little subtle, notice here that you can, for this calculation where you're using a delta T, do you see that a delta T in degrees F is exactly the same as a delta T in degrees R? I'm going to let you study on that, let you think about it a little bit, but a delta T, a change in temperature in degrees F, is the same as a delta T in degrees R. Okay, I'll let you think about that a little bit. All right, so there's our first part 1. Part 2, use the variable specific heat model for air. So all I need to do is go into table A22. 525 is not tabulated there, so I had to write down U at 520 and 537. Those were tabulated, and I had to interpolate to get a number. Same thing. Oh, and right in table A22, I had to have the absolute temperature because that's what's tabulated. So for the upper temperature, the high temperature, I've got 1310 degrees R, not tabulated. Got to interpolate between the 280 and 1320. And so I've done that there. And so U2 minus U1 is simply, again, plug and chug, 140.259 BTUs per pound. So we'll look at the pre-work that we did to get this result. Okay, here is table A20, looking for a single value for C sub V. Here's our initial situation. We don't look at that. Okay. Here's our average situation. So this is what we're interested in. And so we're going to need to interpolate between 0.176 and 0.179. And here's our upper temperature. But the reason I circled them is notice how the numerical value for C sub V does change as temperature gets dramatically higher. So there is some change, not a great deal, not a dramatic, not doubling, but there is some change in C sub V. But just to illustrate, we got to pick a temperature in order to get a single value for C sub V. In this case, we picked 457.5 and had to interpolate to get that CV value. Okay, now moving on to our air with variable specific heat. This is what we did. We see air, table A22E, okay. Our initial temperature was 525, so we had to interpolate between these two numbers. And then we had a really high temperature, so we start looking in A22, and notice here sort of this double column situation. It's so hot, T is so high, we're over on the right-hand block of table A22. We're in between 1280 and 1320, so we've got to interpolate between those two to get our numbers. Okay, I hope this helps. I hope this helps you get started. So let's do a comparison so that we're asked to compare. So we've got 135.45 for delta U on the constant specific heat model. We've got 140.26 for delta U for the variable specific heat model. And so if we consider the bottom number as the baseline, okay, which would probably, a lot of students say, well, which one is correct? I've got two different numbers. Which one is correct? It does make sense that using variable specific heat would probably be the more exact answer. So if we use that as the baseline, our difference is we're only off by 3.4, around 3.5% using either model. So that's not a lot. That's not enough to get excited about in engineering practice, but it can be a lot to be excited about in a high stress quiz or test situation if you were directed to use one model and you used the other. So just be aware of that. Okay. There are other situations where there can be dramatic differences in the model for constant specific heat or variable specific heat. So there can be dramatic differences. Okay. We are getting near the end. I want to address some classic student misconceptions so that if you can see, all of us are tempted to say these things. We're all tempted to do this. So I just want to address these misconceptions, maybe to head you off at the pass. Classic student misconception number one, C sub V is only used for constant volume processes. That is not true. That is a false statement. You can use C sub V whenever you want, okay? As long as you, you can use it for any substance, okay? For an ideal gas, C sub V is a function of temperature only, and you use C sub V when you're trying to find delta U. So let me circle this. So that's the key. It doesn't matter what kind of process you have. It can be constant volume, constant, it can be constant pressure, it can be constant temperature, it can be extraordinarily wild variation in all of those. It can be all kind of things, but you can use you use C sub V for any process of an ideal gas when you're seeking delta U. Same thing for CP. Here we go. The next misconception is C sub P is only used for constant pressure processes. Not true. You use C sub P when you're trying to find delta H. Okay. Simple as that. Okay. And that's so this is a false statement. CP is only used for a constant pressure processes. That's not true. This is true. You use delta H when you're trying to find delta H. That's when you use C sub P. Now, sometimes you use it as a constant number. Other times you use it as a variable, and you're either using tabular work or you're integrating the formula yourself. Okay. But anyway, you use C sub P for all kinds of different processes when you're trying to find delta H. Okay. Here's another student misconception is a lot of students will try this in homework problems. What they'll do is try to say U2 equals question mark. What's a value for U2 only? U2, and well, if I'm going to just take C sub V and multiply it by T and get U. That is not correct, because look at the original definition. Delta U is the integral of CV dt, okay? And so if it's a constant, delta U is equal to CV times delta T, or U2 minus U1 is CV times T2 minus T1. And so do you see that mathematically, you can't say that U2 equals CV times T2. You can't say that U1 is CV times T1. It's only in the difference, okay? So these two, it does not work. H2 does not equal CP times T2. So you think about, you think about the math. So you cannot get a single value for U by taking a specific heat times a temperature. That doesn't work. And so finally, the final classic student misconception is once we introduce the ideal gas equation of state, PV equals MRT, you can generate a jingle for an ideal gas that's a closed system. P1 V1 over T1 equals P2 V2 over T2. The only time you can say that is when you have a closed system in an ideal gas. In other words, MR equals constant. Mass is constant. Mass is fixed. R is a constant for, okay. So this little jingle, P1 V1 over T1 equals P2 V2 over T2, holds only for ideal gases in a closed system. So I can't tell you how many times students try to use this little jingle for steam, for refrigerant. They just love it, but that's an incorrect application of the jingle because you're not remembering what are the restrictions on the jingle. Closed system, ideal gas. So that's what I've got for you, folks. I threw a lot of information at you. I'm hoping you use this video and maybe the accompanying PowerPoint to keep yourself straight in dealing with delta U and delta H for ideal gases. And that's the time that you're using C sub P and C sub V. Okay, and so we're out of there. I'm going to stop recording and wish you good luck in all your problem solving with ideal gases.